Let's work a couple of examples where we will use some of the techniques that we would use if we, say, were a little stuck and wanted to build a bond graph algorithmically. And so in a system like this, it's mechanical. So we've got, what we want to do is, it's translational. We want to identify what we would say are points of velocity. So this is a case here that we're going to assume is rigid. We've got a moving ground here. So this is a seismometer. So the case is attached to the ground. There's obviously motion here. So we've got one velocity here, which is the ground motion. But we've got another velocity which is distinct from that, which we're going to call v sub m. Right, and that's the motion of the mass. So those are seemingly the only two velocities here, except you have to think about another velocity that exists, and that's the difference between that velocity and the ground velocity. And so we know we're going to have that difference that we have to create. And so let's build our graph that way. All right, so let's begin with putting a 1 down, which is our ground velocity. All right, so we'll go ahead and say this is our ground velocity, and we know we're going to attach a source element because we're going to say that there's an input coming in here, but we'll do that in a second. There's another one that we want to put down also, right? Because we know we've got a distinct velocity which represents the motion of that mass, and this is again just one motion just in the vertical direction here. So we've got those two, and we want to create this difference. So how do we create the difference? The difference is going to be the difference between the input velocity and the mass. So we want to create another difference, which is going to be between these two. Remember how we create a difference is we put a 0 down there, and so we have to put sign, and the sign is important. And I know that I want to have the difference I want to have is say some delta v. And by the way, that delta v is the difference between the ends of these elements, which is key to us. And I'm going to show you that that's also the velocity that's important for this sensing element, and I'll talk about that shortly. But that difference is the v of g of t minus v sub m. So we're creating that here, aren't we? See that difference? And then I put a 1 here because this is that difference. And can you see how it might have been intuitive to some people to do that? And in fact, whenever we have two motions and spring element and damper in between, this is a construction that is very useful. So we're going to attach, because we know that the velocity of the spring and the velocity of the damper are the same, and they're equal to that velocity represented by this 1. So that's where we're going to attach our spring element and our damping element. Okay, so that little flow difference construction is key. So let's now attach those elements. Okay, so let's first attach a velocity source, which is the flow source vg, and now I'm going to specify that's a function of time coming in. And then this velocity is the velocity of the mass, so I'm going to go ahead and attach an I element here because that's the velocity of my mass, and I've got some m here. And by the way, if you wanted to put gravity, you could attach that here, right? And because gravity is working, say, down, it's going to work against the velocity. So in fact, the sign is going to be this way. So I could have an effort source attached, because remember, that's acting on that seismic mass. And so there's your mg force attached at that velocity, right? And now I'm going to attach, and I want to leave some space here because I'll show you in a second. I want to have the spring and the damper on that same 1. I hope you can see that now. By creating this 1, we can say, oh, that's the damping force, that's the spring force for these two elements that are inside the seismometer. Now I've left some space here, and why? It's because you've got to know a little bit about what this t means, and I'm going to change that t, and I should have done that in the figure and change that to an r. And usually you need to have some information about this, and what you have there is basically a coil with a magnet moving inside it, you know, and say north-south. And so as this moves relative to, say, a fixed coil, you're going to generate a voltage here. And that's what that E is there. And that's, right, working by this transduction. And you'd need to know something about this. And that's what that T represents in this particular problem, is you would know that my voltage generated here is some constant R times the velocity that this magnet, and that's a permanent magnet, is moving relative to this coil. So I'm going to call that V sub R, because it has to be, and that's why I put a little ground here. I mean, the coil's not moving. That VR is the relative velocity between the permanent magnet and the coil. I hope you can see where I'm going with that, because that relative velocity is the velocity between the mass, which has the magnet attached to it, and the coil, which is attached to the case. And you can see that that's that velocity here. This is the relative velocity that we just found. Right, that's V sub R. So when you're thinking about attaching that sensing element, you need to consider this. And look at that relationship. It says that a voltage, an effort, is related to a velocity or a flow. What kind of element does that suggest to you? Gyrator. So that gyrator, I have some relative motion generating some voltage with some constant R. Okay, so put that right there. And that is the relative velocity generating some E. Now finally, you need an element that you would attach, you know, this electrical port to. It's been left open here. So let's say, and remember we talked about different types of ways to represent things of this sort. Let's say I wanted to put an ideal, let's say, voltage amplifier. I want to measure that voltage. So if this was a voltage amp, right, then it's going to give me an amplified voltage out. It's going to give me a amplified voltage out. Let's call it E out, relative to some input voltage E, and the current that it's going to draw. This is an ideal voltage amp. Do you remember from basic op-amp circuits that current is about 0? So I can represent a voltage, remember an ideal voltage amp, by assuming that I'd have an ideal conversion. And so I can just represent that with a flow source and say that this current is about 0. And then when I want to amplify it, I can just say, okay, here's my E, and then I'd have some out that's some constant K times E, and then I can just say that my voltage amplifier has that K value, and so this is my little amplifier equation for that. And then remember, E is related to V sub R, to this equation. And the neat thing about this is, remember, gyrators have two equations. They have a voltage, a force here also, and then the current. If that current is 0, that means that force is 0, and that's something that you would see when you derive the equations. But I'm going to stop here. Later, when we derive some equations and related problems and related exercises, we might come back to this bond graph, and I may ask you to derive the equations or use this in some other kinds of analysis as we start looking more towards system analysis of problems of this sort and answering specific questions about a system. But now, before we go away from this, we've laid out a lot of different concepts here. Rewatch this and think about it again. Think about the construction. This was the application of a situation where you maybe could not see, how do I interconnect all these elements? Construction of a flow difference, or here in this case a velocity difference, right? And I can assure you it's a little trick that you can use quite a bit when you're building mechanical system models. and practice it, and it'll be very helpful to you. And one other last point about this simple little graph is that we haven't applied causality, but remember you've got this little construction here. If you wanted to leave that one there, you could. Otherwise, you could collapse this. You remember you have the tube, the power is flowing into a one and out, so you could eliminate this one, and basically the flow would be right into that zero. So that's another thing that you could do to reduce this before you apply causality. Okay, here's this little torsional coupler example that we talked about in the introduction to algorithmic conversion methods. And let's go ahead and build a graph for this. And this is a mechanical system. So again, what do? We identify distinct velocities. So where are the distinct velocities in this case? Well, we always look for, to begin with, mass elements or inertial elements. So there'll be the translational or rotational. And so, we've got one omega here, we've got another omega, here, we've got a low torque applied on that omega. And then remember, if we assume that this shaft is rigid, then it's at the same velocity. But the key here, and again, sometimes for some people these things are easy to see, for others are not. And I hope you're going to see that this system is a little similar to the one we just worked, except there's torques input in rather than velocities. But again, because of the construction, it can be a little tricky to see. So, but there is a distinct velocity that's between these two elements, and that's where we're going to attach that spring. And depending on how you model this shaft, if it's rigid, then the velocity at that point, which is now defining the relative velocity between that rotational element and the shaft, which defines where you would attach that damping, that's another velocity difference. And think about it, and I hope you can see it's the same velocity difference as between those two elements. So again, if you can see all of that, maybe you can draw it by inspection. Otherwise, what do? Well, you drop it one, and you say this is, and let's call this omega 1. Let's call this one omega 2. Okay, and that's omega 1, and that's omega 2. Okay, and remember, once you drop that down, then you say, oh, that's where I attach this torque. That's where I attach that torque. So you could attach those torques on there. We'll do that at the end. And this is where my mass element is attached. So you can do that right now, just so that you can remember, oh, this right here, that's where my, I'm going to call that J1. This is my J1. And let's call that J2. Let's go ahead and attach those inertias if you like. Now we need to build a flow difference between these two. And hope you're starting to see that with mechanical systems, this construction is very common, this flow difference construction here. This omega 1 minus omega 2, I'm going to call that just omega here. That's the difference between those two velocities, which is going to be where I'm going to attach my, not an I element, it's a spring. That's a 1 over k, isn't it? And then the damping also is attached there. Now, you could have built this in different ways. Some people like to treat two different paths, and you might see that in other references where you might have one of these differences attached to C, another difference attached to R, but it's equivalent to this construction here. And again, once you see this, you can maybe start drawing it by inspection, but if you can't see it, then again, falling back and using this flow difference construction can be very helpful. Lastly, attach torques. If the velocity is working this way, this is working against it, then you can see hopefully that effort is going to be taking power out, and that's my low torque out here attached to that mass, and then you're going to have one effort coming in here, which is my input. Okay, and that would be your graph. Now, the reason the flow difference can be, an algorithmic approach and using flow differences can be helpful. Let's say I change the problem on you and I said, something that shaft now, has some compliance. Your model is going to change. You might leave that for an exercise for you. Remodel this system, but now consider that that this shaft here has some stiffness Ks, or is compliant. Remember, compliance is just the inverse of stiffness, right? That's shaft compliance. That might hopefully be a familiar term, but for some people, shaft compliance is just the inverse of the stiffness. Try to rebuild the graph now, assuming that, and you can see now there could be a difference, and it maybe even put a torque on the end there, and you can hopefully see that the system becomes a little bit more complicated, and using algorithmic methods sometimes helps you keep track of all those subtle differences. Let's take a look at this example where I have a rolling wheel, and let's assume that it could slip, so there could be some slip here, but I'm pulling this. It's almost like a yo-yo, right, where you're maybe pulling it with a force here, and so the tricky thing is you've got to see, okay, the radius to this point here, so there's a difference velocity between here, and also there. So how do you model the system where you could take into account all the different forces? Because remember, if you built a free body diagram for this, you'd also have a force at this slip element. Okay, so step one, maybe I'd say, oh, I've got a distinct velocity, translational at that point, and I'm going to drop that guy. Oh, but I also have a rotational velocity, and I don't know how I'm going to connect those yet, but I'm going to drop that one down here. Okay. Finally, I know I've got a difference between, let's say, this translational velocity and the one at this point where this force is going to be attached, right? And that string could be slipping on there too. So, but a force is being attached there, okay, and I'm pulling it at that point. And so I'm putting that one there. So you can see that that's a difference. And so I'm showing you the construction here, how you can connect all those things. But in order to get the difference velocity that you need down here, that's the difference, is you need to take r omega, translate it through a transformer, and then you've got this little r omega here, and now you've got that difference v minus r omega. So you see how in this case you've had to use a transformer to translate from the rotational degree of freedom of this wheel into a translational domain, and now you can find a flow difference. Okay, this is a little tricky problem. Again, everybody's experience is different, so it might take a little while to kind of work through it a few times, and before it really sinks in. So now you've constructed that piece, and now what do we do about connecting the rest of the elements that we need? So now in this slide I'm showing, remember, I've taken that first piece where we constructed this flow difference here using the transformer, but now I need to model the slip between the wheel turning omega here, and then there's a radius r there, and then the ground, right? So but this guy's moving v there, and I need a velocity here, and that velocity difference is v minus r omega. So just it's in parallel to this guy, I've constructed it, right, with a different r now. Now this is the radius of the wheel, this was the radius of the hub, if you like, and now I've constructed here that r omega. Here's v again, and now I've got this wheel slip velocity there. Okay, once I have this constructed, then I can start attaching things. So move over here and see how that slip velocity, I can now attach a resistive element, and that's I call that my slip R. It's the friction at that interface, right? And at this one I want to connect a force, and I want to put power in. So note how, again, here's another nice example of how you're not going to be able to take that one out, although this one you could take out. Finally, we could finish this by attaching the inertial elements here. This is the translation of the mass. This is the rotational of the wheel, right? And again, you could take these out if you like. The eye would just be attached there, and that would, and this one as well. This could collapse there, and then you'd have a little submodel for a wheel being pulled by a string. Apply causality, derive equations, or attach it to a larger system. One final example, and I'm not going to work through this one completely, just maybe get you started. How would you handle a system like this? We talked about a system that had translational, mechanical, and rotational systems. Here now I have a hydraulic system, and again, I may post some other examples with electrical and so on, but remember with mechanical systems, you would identify velocities with, and that's for translation or rotation. If you have every other kind of system, which is electrical, hydraulic, thermal, and even magnetic and chemical, if you like, all of the other systems, it turns out that the way we can use algorithmic methods is we identify basically effort nodes. So, for example, what makes it easy in this system would be to identify pressure nodes, because that allows us to connect elements that way. Now, this would be a rather complex system, but I want you to see that you could start off by saying, okay, I've got a one junction here where I would put this mass and call that, say, V1, and that's where I would attach a force. But then I would have, and it's very subtle, but this case here, you would lay down another velocity there for, call that V2, and you would construct a difference, and so on. And this difference is where you would attach your spring, say, for starters. You also are going to have to couple into this pressure node. So somewhere over here, as you're building the graph, you'd say, oh, okay, I have a pressure. And how do I connect that pressure to that case? Well, that's a transformer, right? You can see there's an area there. So you would use a transformer and say, let's call that area of area 2, which is the case, say. And you can see that that's going to be pushing against that velocity. So over here there'd be a velocity, and in fact it's going to be the velocity of the case. So you can see how then you could couple the mechanical, again, if you can't see it, directly to the hydraulic, and then so on. And by the way, let's just do one more in the interest of time. I've got another pressure node here and a pressure node there, so I might drop another pressure node over here. And by the way, you might iterate on drawing these and have to erase and so on. I'm trying to do this in limited space here, but you can see that I'm going to have flow going through this orifice. And how would I connect the resistance there? Well, I would need what? An effort difference, right? Because I have a pressure drop there. That effort difference, that's where I would attach my resistance. And I would have nothing else attached here, so I would collapse that. So there's your R, which is kind of like a valve across here. Where things start getting kind of complicated with this little system, and then you could couple then into that pressure to to the motion of that piston. Say that's V3. You need a transformer going into that V3. You can see this is going to be a big graph, okay? But it would then allow you at the end of the day to have a complete graph, and then use the tools that we're learning how to use with regard to causality. Reduce the graph, because you may have a lot of extra ones and zeros. You can pull some of these out, but there will be here, maybe if you start including leakage, there might be flow coming out of this zero, for example, and you would have to model that. So for example, like here I have a seal. If I wanted to have leakage through there into the exit, yeah, see I have leakage, or even leakage from P2 out to here. So this might need another effort difference, right? And this is atmosphere, and there's your leakage across that seal, okay? And there could be leakage here too. And finally, look, you're over here on this one, and now you can begin coupling that velocity here to the velocity of this case to take into account that spring and so on. And finally, you'd construct a larger graph. This is not a simple bond graph. and it would take a little bit of time to build something. But I want to show you it's problems like this where it can help to think about it a little bit and use some algorithmic methods to kind of structure it little by little.